Hi everyone. So today I wanted to talk about expression trees in C#. And the reason I chose this topic in particular is because I think expression trees is a rather interesting and cool feature that exists in the framework and the language. And it has been around for a very long time, but it's so obscure that very few people actually know about it or how to use it, I guess, or what is it even for. And to most developers, expression trees is somewhat synonymous with object relational mapping frameworks or link providers or stuff like this. And while it's one of their more common use cases, it's also not the only one. So today during this talk, we'll look into expression trees more deeply. We'll figure out what they are conceptually and find some of the different ways and approaches where using expression trees can actually provide benefits for us. So first, let me introduce myself. My name is Alexey. I am primarily an open source developer. I also sometimes speak at different conferences, such as this one, and I have a blog on my website where I write about different tech things that are kind of like more on the controversial or niche or obscure spectrum of things. And my primary stack is .NET, so I use C# with Sharp and I also use TypeScript. And the projects I work on are usually in the cloud and web area, and I also do automation DevOps. So by the end of the talk, you'll find that you have some question, and you can always ask it during the QA session, but maybe you won't have time for some reason. You can always message me on Twitter. My screen name is in the bottom right. And if you have any question, you can hit me up, and I'll always be happy to answer. So let's begin, and the first kind of question that we may want to look into, since it's a talk about expression trees, is what is an expression tree exactly? And to answer that, we'll have to dig a little bit more deeply and figure out what is an expression. An expression is basically a fundamental construct in pretty much any programming language, and it represents an operation that does something and returns a value. So on the screen you can see one of those. So 2 plus 3 is an operation that finds the sum of two numbers, and then it returns that, which is in this case is 5. And this operation is actually an expression. And if we wanted to, we could analyze it more deeply and see that it's an expression that is composed of some sub-expressions or some components, which in this case is a constant for 2, constant for 3, and those are basically operands to a plus operator, which signifies that this is an operation that returns the sum of two values. Now, of course, expressions are usually more complicated than that, and we can look into a more involved example. So here we have a conditional expression written in C# whose condition is evaluated by calling a method string is null or white space with some parameter, then negating the result, and based off of whether it's true or false, we either take some constant string and add it to the parameter that we have or variable, or if it's false, we just return null. And there are basically two questions if we wanted to understand what this expression is about. There are two questions we can ask. And the first one is, what does it do? And the second one is, how does it do it? And so if we wanted to answer the first question, it's actually quite simple. All we have to do is kind of imagine that it's wrapped in a function. So the function basically evaluates this expression. And to answer what it does, we can just say, well, it depends on the person name parameter and on some logic that is encoded in this expression. It returns either a string or a null in some other cases. But if we wanted to figure out how does it do it, or like what is the exact logic that it operates using, then we have to analyze this expression in the exact same way that we did with the previous one. And it's also quite simple. So if we look really closely, we'll see that this expression is composed of multiple smaller ones. So for example, operator not, which just negates the Boolean value to the opposite one. There's the method call expression, and then the parameter expression that we pass on to it. For the true clause, we have the constant expression, the add operation, the parameter expression, and then the null expression is also another constant expression. And so if you look at this very closely, you will figure out or notice that all of these components or the sub-expressions, they really make like this structure that represents a tree, or looks like a tree. So alternatively, we could have built it in this way, and we could have the Turner conditional expression at the very top, so at the root of the tree. And for different types, for example, for when it's true, we have another expression that evaluates to, which is the plus operation of two operands. the constant, the person name. For false, it's just null, and the condition itself is evaluated as an expression that negates another expression, which in turn is a method call, which uses the isNor whitespace method with person name as parameter. And so basically this is the tree, which is the expression tree. So it kind of forms the structure that represents what or how exactly the expression is evaluated. And as a general summarization of that, we can say that expression tree is just a model to describe a structure of an expression. So how it's built from different components or primitives. And when it comes to .NET, expression trees are also a little bit more specific to the .NET world. So you can use them to model the different expressions we would normally be able to write using C# or F# or other languages. And all of the different expressions that are supported by the framework are located in the system link expressions namespace. And they all derive from this expression abstract class. And we can create different instances of these expressions using the factory methods that are provided as static methods in this class. Or we can use the compiler feature that can infer the expressions specifically for lambda expressions from code that we write directly in C#, for example. And finally, lambda expressions are also special in that way that they can be executed because they represent anonymous functions. And so with expression trees, we can actually compile them into IL code directly in memory, and then later use them as executable delegates in some other places. So let's look into how to do this, and we'll look into how to construct expression trees manually from code. And as a practical example, we will look into the same expression that we have seen earlier and try to create it using the different factory methods that are available in the expression class. And like I mentioned, the expression class is just an abstract class in the system link expressions namespace. It has all the different expressions deriving from it. It also has different factory methods that we can use, for example, the constant to create the constant expression, and the new to create the object initialization expression, and so on and so forth, and all of the different types, and there are probably multiple dozens of them. So let's look at our example just to remind ourselves what it looks like. This is the same expression we've seen earlier. It has a conditional expression at the root of it, and then for the true clause, it just combines two string values, and for the false clause, it just returns null. So let's create this template function that will just kind of return the delegate we want, and the delegate we want is a function that takes a string, so the parameter, which is the person name, and then returns the string that can be nullable. And so this will be a function that returns a function, and in order to construct it, we have to start with the most base components, so the ones that don't depend on anything else. And the one that we can immediately start with is the parameter. So we can create the parameter expression by using the expression parameter method, and then specifying the type and the name, and that creates an expression that we can use to basically link the value from the parameter to other places, or even set the parameter value from like a function. So for the conditional expression, which is the expression that checks whether the condition that we want to evaluate is true, we want to call the string isNor whitespace method. And to do this, since we're doing it dynamically, we have to get essentially the reference to this method, so the method info. And to do that, we can use reflection. So by calling type of string get method, we can get that method info we talked about. And once we have it, we can use expression call to execute, or rather create an expression that executes this method with the parameter, and then produces the expression that we also have to negate, because we have the not string isNor whitespace, so we have to turn it to the opposite one. And so for that reason, we also wrap it into expression not, which basically just represents the unary exclamation mark operator. And that condition expression is basically done, but we also have the true clause, which is what happens if the condition evaluates to true. And in that case, we just want to take the greetings literal and combine it with another string, and we can use the expression add operator to do this. And finally, for the false clause, all we have to do is return null. And to do that, we can also use expression constant. However, we also have to specify the type here because all of the branches in the conditional expression have to have the same type, and null doesn't actually have any specific type, so we have to sort of give a hint to the compiler what it is. Now finally, since we already have all the parts completed, we just have to combine them together. So we have the expression for the condition, for the true clause and the false clause, and we can put them all into expression condition, which returns the conditional expression. And just like this, we already replicated the expression that we've seen earlier. So we have the expression tree for it, which starts with the condition, then goes into condition expression, which is evaluated through the not operator, then the call to a method, and then for the true branch, and so yada yada yada. But we can't actually use it for anything useful here because we constructed it ourselves. We don't really want to analyze it. What we want to do is wrap it also in lambda expressions that can be executed. And to do this, all we have to really write is expression lambda and then specify the generic type for it, which is the type of the function that we want this to represent. And then pass the body of the function, which is the conditional expression that we have, and the parameter. So now the function that is represented by this expression has a parameter, and that is the same parameter that is used in other places, such as the when we pass it to is null or white space method, and also when we concatenate the greetings constant. Now once that's done, we can also take that lambda and compile it into runtime instructions. And to do that, we can just use the compile method, and that returns the delegate of type that we specified in the generic arguments. So now we can use this construct greeting function method to return us the get greeting delegate, and we could try to run it, for example, on John, and we would expect that it would return greetings John, as John is not a null or white space string. However, instead we actually get an error at runtime that says the binary operator add is not defined for the types system string and system string, which might be a little bit confusing because we have, programmed all our lives in C#, and well, we could always do like one string plus another string and it always worked, but why is it not defined? And in reality, it's not actually defined. So if you look into the .NET sources, you'll find that system string does not have the plus operator. And the way it works actually is that the compiler just takes your plus operators and then kind of merges them together and turns that into a call to string concat method. And since we were trying to compile the expression tree ourselves, we also need to essentially do, turn into the code it ends up being, so we have to call string concat directly. And that's actually pretty simple. All we have to do is get the reference, like we did this is null or white space, and just get the method that represents string concat with 2 arguments. And then instead of expression add and for the true clause, we just replace that and set expression call with that method and with the same parameters, which is the constant and the person name. And now that we've done that, we can actually get the delegate again, try to use it on John and then some white space string, and we'll get the results that we expect. So we get greetings John for the first one, and then we just get null for the second one. And that's pretty cool. What we've done is basically we constructed an expression tree in code, run dynamically at runtime, and then we wrapped it into a lambda expression. We also compiled into runtime instructions, which is basically IL code, that we can execute in other parts of the program. So to us, like from this perspective, it looks as though getGreetings actually is just a delegate that is defined somewhere in C#, but it actually comes from runtime. So it's not specified in the, with the rest of our project. We generated it dynamically. And while it's cool, it also like begs the question of why would we ever need that? And one of the more common use cases for expression trees that are compiled to delegates to runtime instructions is to optimize reflection-heavy code. So as you may know that whenever you use reflections, there is a pretty relatively heavy cost that it incurs. So if you use that in some critical side loops or some method calls that are expected to run really quickly, you will probably not be very happy with the way it performs because it has some performance downsides. So let's, for example, imagine that we have a class called command, and that class also has an execute method. And that execute method just happens to be private. It's kind of like for the sake of this example. And just to have a reason to use reflection, let's imagine we want to call execute from outside of this class. And how can we do this? Of course, we can use reflection, so we can use the same approach as we did before. So get the command type, then get the method, and then invoke it with the parameter, and that just works. Of course, like we mentioned earlier, it's kind of slow, well, relatively to some other approaches we're gonna see soon, but it works. And actually, we can even improve the performance of it without resorting to compiled expression trees, simply by, for example, caching the method info that we get through reflection. So let's try to do that. And to do that, we can just have a static property, like just in general a class that has this reference, and because this property is assigned as a static initializer, essentially, it's only going to be evaluated once, and once it's evaluated, it just stores the reference inside of the property. And so in order to call the method, we can just use that method info that we have cached and invoke it with the parameter. But even that is not enough. We can actually go further beyond and use delegate create delegate, which is another kind of obscure API that allows you to create a delegate from a method info of a specific type. So the way it works is that you take a method info, you give it to delegate create delegate, and you also specify which type of the delegate you want to have returned. And once that's done, we can just reuse the same delegate all the time, so we also can cache it, and then the call execute just basically calls that delegate directly. And of course, since we're talking about expression trees, we can also do the exact same thing but with expression trees. So just get the method info that represents the execute method, and then use the static initializer to compose the expressions that represent that expression call, the method call. And so to do this, we also have to start with the parameters. So every instance method and execute as an instance method has to have one parameter at least that specify what instance does it run on. And here it's just of type command. And we wrap it into expression call to signify that we want to call this method with that instance. And once we have that, we can just wrap it into a lambda expression and compile it into delegate. So once we have a delegate, it's pretty similar to delegate create delegate from the previous slide, and then we just call it directly in the call execute method. And this approach, where we basically initialize, or I guess compile the expression in a static initializer, is what I like to call lazy thread safe initialization via static constructor. And the way it's helpful is because it only happens once, so the static initializer is guaranteed to only execute once, and it happens the first time that any of the members from this class are referenced in code, or like used directly in runtime. And it helps us with caching because we don't really want to compile the expression all the time. I just want to do it once. It doesn't change since then. And we want to also just do it once and kind of forget about it and don't want to worry about any thread safety issues. And static initializer helps us with that because it's just taken care of by the runtime. And so now that we have all of that done, let's put all of these approaches against each other in a benchmark. So we have the reflection approach, the cached approach, which just caches the method info. Then we have the delegate create delegate, and then finally the expression trees, and see which one is the fastest. So I already did this, of course, and the result is that, of course, reflection is the slowest. The caching helps a little bit, but it's still magnitudes slower than, for example, delegate create delegate and expressions. And delegate create delegate is actually really fast because it works somewhat similar to compiled expressions, but it also has some limitations. So for example, we can't use it on constructors and some other stuff, while expressions can be used to represent almost anything that we would normally be able to in C#, for example. And also, besides that, expression trees are also a little bit faster than delegate create delegate. So whenever you have basically context where you work with reflection and you want to make sure it runs quickly, that like if you use it in a tight loop or somewhere where the performance is critical, you may want to look into expression trees because compiling them in memory in runtime can yield you a lot of advantage in terms of performance. Another way we can use compiled expression trees is to implement generic operators. And so first of all, let's start with a simple example. Let's imagine we want to, or we have a method called 3/4, which just calculates 3/4 of a value, and we have it defined for an integer, which just a function that takes x, basically. And it just so happens that we also want to extend it to support other types. So for example, we want to support long and float and double, which all would work differently, but they also would have the same code. In order to do this, we would just have to write them multiple times and create many overloads. So we would have one for integer, for long, for float, for double, for decimal. And we already have 5, and that's not even covering all of the numeric types that are available in, for example, C#. And that's also kind of tedious because we have to duplicate our code, and it can easily be a lot more complex than this, and any code that also relies on this code will have to have branches or like also some duplication and whatnot. And ideally, we want something different and something that looks like this. So we want to have a method that's generic and just works on any numeric type, and we just use the same expression and it just works. Unfortunately, it doesn't. You can't do this in C# because, well, first of all, this doesn't compile. If you try to do this, we'll just tell you that not every t that can be used in this method is actually one that defines multiply and divide operators. And also, C# doesn't have any generic constraints that could be used to tell that this method only works in numeric types. So C# is kind of limited in this aspect. But we can also use compiled expression trees to represent essentially the same thing. So let's start with the method that we want to, the method signature that we want to achieve. So 3/4, which is generic, and we have this parameter x, so we have to represent that using expressions. So as usual, we start with expression parameter type of t. The name is not relevant here. It kind of just gets generated automatically if you don't specify one. And then we have to define the constants for 3 and 4. But the important thing here is that we have to make sure that the 3 and 4 constants have the same type as t. Because even when you write code like, for example, 2 times 1.5, which looks like you're multiplying an integer by double, what happens is that the compiler turns into 2.0 times 1.5, so it turns them both into double. And we have to do the same thing ourselves. So here we just take the constant like 3 and 4 and convert it to the type of t. And once that's done, we can express the operation that we want to perform, which is to multiply that parameter by 3 and then also divide by 4. Doing this means that we have to build this kind of expression tree already. And then once that's done, we just need to wrap it into lambda so we can execute it, compile it, and then return the result of that function. And now if we want to call this with different values, for example, we can use 3/4 18, which is an integer, that will return 13. If we use a double 6.66, it will return a double as well. And that's the same for decimal and basically any other type that has the multiplication and division operators defined for them. And that's very nice because we essentially did it once, so we can kind of just have expressions, for example, for every operator and reuse them in our code if we want to make it work for any numeric type, for example. But there's also one little problem in that it only checks the type at runtime. And so here, for example, if we pass in something else, let's say datetime offset, which doesn't have multiplication operator, the code will throw an exception. And because of that, we can ask that, well, how is it any different than just using the dynamic keyword? And the answer is, of course, that we can use the same approach that I've shown earlier to make this thing a lot faster than dynamic. So if we just have create a static class for it, and because it's generic, have another class with a static initializer, use that to compile our expression into a delegate, we can make sure that it only happens once by doing it using the same approach. It's also thread safe and it's cached, so all of the costs will be incurred only once. We can improve performance quite a lot. And to verify that, let's run another benchmark. So we'll have a static multiplication division, so just typing it in code directly. We have the expression trees, which we just showed, and also the dynamic multiplication, so just using the dynamic keyword to kind of forget about static typing for a moment. And if we run the benchmarks, we will see that static, static code obviously executes the fastest, but the expression trees are not that far off. They're actually pretty close, especially if you compare them to dynamic, which are 20 times slower almost. So basically, in this case, there are not too many options. You can either use dynamic or expression trees, and expression trees are significantly faster as well. So whenever you have this weird combination that you need to use generics with operators that is normally not possible in C#, you can resort to compile expression trees to get the job done and at the same time be quite performant as well. Another use case for manually created expression trees is parsing DSLs. And parsing is usually a pretty complicated endeavor because you have to take some text, you have to turn it into some model that represents the different syntactic components, but then you also have to have an interpreter that analyzes the model and turns it into runtime instructions and so on and so forth, which is actually quite difficult. And in many cases, we can just parse the text directly into expressions. And because of that, the interpretation part has already been done for us by .NET. We can just compile them in memory and run them and just have the .NET framework take care of that for us. So let's look at a simple example. Here we just have a class simple calculator. The way it works is that it has a run method, and that run method just takes an expression as a string. So we can type in 2 + 5 or 3 × 11 or even some longer and more complicated expressions. And then it parses that, evaluates this as a mathematical expression, and then returns us the result. And the way it works is that I have this parser built using Spresh, which is the parser combinator library for C#, which is kind of useful. And I have a parser defined for the constant, so numbers like 10 or 15 or 2. And I use the decimal invariant primitive for that and just turn it into double, and then map it to an expression constant. So whenever I have a number that I see in text, I just turn it to a constant expression straight away. And then for operator, which is basically the character that represents different operations that we can do, for example, plus, minus, multiply, or divide, I just have a simple parser that looks for those characters and returns an expression type. An expression type is basically an enum, so it's also defined in system link expressions for us, so we don't have to do anything ourselves. And we can use it further with the operation parser that takes the operator and constant, chains them together, and uses expression make binary factor method as a reducer. So whenever it accumulates some expression, it basically uses the operator that we found, which could be add, subtract, multiply, or divide, and it makes that into a recursive binary expression. Then once we have that parsed, we can just wrap it into a lambda expression as we've done before, and compile it and run it and see what it produces. So we can run it on some examples. So for 2 + 2 returns 4. For something more complicated, it also works correctly. And while it's pretty simple, it actually gets the job done. And the advantage here of using expression trees is that we didn't have to define any abstract syntax tree for the model. We didn't have to make our own interpreter to see how the different syntactic components should be treated together and so on and so forth. We just parsed directly to expression trees, and .NET did all of the heavy work for us. Now we've looked into expression trees that could be constructed manually in runtime. There is another way to obtain them, and that is to get them from lambdas defined in our code. And this is the method you're most likely familiar with. This is the one that's used in ORM frameworks and so on and so forth. And the way it works is basically here we have 2 variables, and they're named div and divexpr correspondingly, but they assign the same value, but they're of different type. And so here you can see that the first one is actually just a func, which is a delegate type, and the second one is the expression of that delegate type. And while we assign the same value to both of them, they actually have completely different meaning and semantics. And so with the div expression, we can actually look into what type it represents, and we'll get the same delegate type that we see above us. We can also, for example, look through parameters and see what kind of parameters it has. We can analyze it all kind of different ways. And at the end of the day, we can also compile it, and when compiled, it will get the same delegate that we see above. So we can go from the later to the former by just calling compile. And so because of that, we can see that the expression at the bottom is kind of like a recipe for the delegate at the top, which is the product. And there are some limitations to this approach, so although it's kind of cool that we can do that, we cannot always do this, and this is in contrast with manual constructed expressions that can be used to represent almost anything we would normally be able to do. With expressions obtained in such way, there are some limitations. So for example, if we have a delegate defined and we want to kind of assign it to expressions to hopefully get it decompiled automatically, that won't work, because that produces a compilation error. Additionally, the expressions that are obtained in such way cannot have multiple statements. So for example, here I have a result that is kind of like stored in a variable and then returned. You can do that with manually constructed expressions, but if you try to do this like this, then it will also give you an error during compilation. And this is even more important when we have statements, because even in case of with expressions, we can kind of like merge them together and have return statement just return the a divided by b straight away. With the second one, we can't really do this because there are separate statements that cannot be, merged into one, and we cannot express them in such way. There are also other limitations which are based off of the different C# features that are not supported. So stuff like null coalescing operator, the dynamic keyword, async await, name it optional parameters, the out parameters, and all that kind of stuff. All of this is not supported. So whenever you have a delegate that uses something like this, we will just get a compilation error and it won't work. And the reason is that because this kind of approach where the compiler infers the expression trees automatically was essentially built for the purpose of link queue providers and ORM frameworks, and it's used to just get the expression and turn it into code like a SQL, for example, and stuff like that. And that was added a long time ago, and since then C# had seen a lot of new features added as well, but they never were introduced into this kind of approach for inferring expression trees automatically. So unfortunately, we cannot use that or do that, but there are still some really cool things that we can do with the expression trees obtained in such way. And one of the more common use cases is identifying type members. So expression trees, or expressions, I guess, they help us identify type members. So basically just a meta-programming in a statically typed way. And to explain what exactly I mean, let's look at a simple example. So here we have a class called DTO, and this class has two properties. One of them is called ID, which is of type GUID, and then we have name, which is of type string. And let's assume we, for some reason, want to get the property info of DTO ID. And to do that, we can simply just use reflection. So we can just get the property using type of DTO, get property name of DTO ID, and that works, and we get all the information associated with that. Let's imagine we actually want to use that to build a validator library, so some kind of class that allows us to add some validation rules for different properties of an object, and then finally, once they're added, call a validate method that executes them and sees if a specific instance of that class is actually valid. So to do that, we can have an add validation method that takes a property name and also has a predicate that works on that property to check if it's valid or not. And once we have the property name, we can use reflection to get the property, and let's assume we have something else there that just does all the magic required. That is not really relevant to us here. But for us, as users of this library, we can, for example, create this validator and add some validation rules for our DTO. So let's say we add the validation rule for the GUID. We configure the DTO ID so that it cannot be empty, and then for the name, we configure it so that it's never null or white space. And for example, we can test it on some instance which doesn't have the name set, and it will return false. The problem, however, comes when we decide to change the property type, for example. So if we, for example, decide that DTO ID should not be GUID, but it should be an integer instead, when we change that, none of our code stops working. In fact, the validation rule that we've written for ID that uses this comparison with GUID empty will still compile and seem to work as expected, but it will throw an error during runtime. And that's not good. But we can avoid this problem entirely if we just use expression trees. So instead of using the property name as a string, we can just use an expression parameter that evaluates to an instance of that property. So basically, we kind of just pass a function that takes an object and returns the property that we're interested in, but we are not actually going to evaluate that function. We just want to understand how it's structured and how it works. And once we have that expression, we can try to cast the body to member expression, which is the expression that references some member, and see if it's a property. And if it's a property, then we can do the same thing we've done previously. But the difference now is that as a user, when we call the addValidation method, first of all, we don't have to specify the generic type, because now it can be inferred from the expression, since it's statically typed. But also, when we decide to suddenly change the type of the GUID from GUID to int or vice versa, it won't let us just silently compile the program. So if we decide to do this, the delegate that returns the DTOID, which is kind of just used as an expression, will identify that the property is of type integer, but the delegate that uses to check whether the property is valid assumes that it's actually as of type GUID because it compares it to GUID. And that will give us an error during compilation. Another cool thing we can do with the expression trees obtained in such way is to preserve the source code in runtime. That can be useful, for example, in test assertions. So let's assume that we have this task that just runs, executes int try parse with some string and returns some value, and we want to make sure that it works correctly. So we have two assertions. The first one checks that the result is true, which has to be positive, and also we check that the value is equal to what we expect. And to make the error messages in case of failed assertions more informative, we also provide some error, information that saying that parsing was unsuccessful or pass value is incorrect. And that helps us because whenever the test fails, we can see from the error message what exactly went wrong. So here we see that, oh, the value is incorrect. So it did return true, but some other part has failed. And that's kind of useful. But it's also a little bit tedious, and instead we want to be able to just have the code that we use to write the assertions just displayed here, because that would give us enough information to understand what exactly has failed. And we can do this using the expression trees. So we can have a helper class assert x that takes an action expression, so the one that doesn't return anything, and then we can compile it and execute it. And if that returns, or rather throws, an assertion exception that means that the assertion has failed, we want to extend that and rethrow it by adding the body of the expression that actually failed, so the assertion that didn't go as we expected. And to do that, we also use this extension method called toReadableString, which turns an expression, and it works with any expression at all. It turns it into C# code that is humanly readable and looks as though it was actually written by a human. And this extension method comes from a separate package called Readable Expressions, which you can find in NuGet. Now when we have that, we can replace the assertion part of our test with the assert x express, and then use the same thing without specifying the error message. And now whenever the test fails, we can also see the exact assertion that has failed. So now we can also see that the value was supposed to be equal to 1 to 4, but it wasn't. And it's immediately clear which part of our test has failed. We can even go a step further, and for example, instead of using an units assertion directly, we can have, for example, assert x express and then result equals 1 to 4, and then use the expression trees to analyze that and see whether it's like a Boolean comparison or something like this, and turn that into unit assertions and make a really powerful testing frame. So this is just one of the interesting use cases for expression trees obtained using this approach. Another one is, of course, since we get expression trees from all kinds of places, sometimes we just want to traverse them and analyze them deeply. And since it's a tree, it will have nested hierarchy. And sometimes we just want to see and understand what that tree and hierarchy represents. And to do this, there is a helpful class called expression visitor, which is also in the same namespace, system link expressions. And it's also extract. And it functions by just basically providing the different virtual methods for every type of expression that exists, which allows us to derive from this class and implement the different visitors. So for example, let's assume we have this visitor class that derives from expression visitor, and we just override visit method call and visit binary. So whenever we stumble upon a method call expression, we will just write that to console, and whenever we see a binary expression, we also write that to console too. And to see how it works, let's just see what it provides us with when we run it on this simple expression. So I just created some convoluted expression for the sake of the demonstration. I have a math sin, new GUID get hash code divided by 10, some kind of nested expression tree. And then when we run that visitor on that expression, we will see in the console that it first stumbles on the binary expression, which is the topmost, which is the result of the left expression divided by 10. And then it goes inside, it stumbles upon a method call to math sin, and then it goes deeper to get the get hash code on new GUID, and finally we have the new GUID method. So as you can see, kind of traverse them in a recursive descent manner. But we can actually use the visitor for something cool. So as you can see, it returns an expression. So we don't have to only use it to analyze things and see what the expression is made of, but we can actually rewrite it. So in this case, I just overridden the visit method call method, and I told it to whenever it stumbles upon a call to mass sin, I wanted to replace that with mass cos. So whenever I have a sine calculation, I want to replace it with the cosine. And to do that, I just use expression call again, change the method to a different one, and use the same arguments. And again, if I use that expression, so the first time I run the expression normally, where we have this convoluted expression from the previous slide, we get some result, and we can see that if we use the readable string, we will get the exact thing that we wrote. But when we when we use the visitor that we created and run it on that expression, we get a completely different expression where the sin is actually replaced by cos. So just like that, we were able to replace one method call with another. And we can actually use it for something much more intricate, for example, rewriting an entire tree. And this is actually how the popular mock frameworks work. So whenever you specify some expression that represents a method call, it rewrites that into something completely different. Okay, so another thing we can do, since we can transpile, since we can kind of just traverse the tree, we can also transpile it to a different language. So we don't have to return expressions. We can build some strings that represent the same code, for example, in a different language. So for this to show, let's look into a very simple expression that I will be using and specializing on. So this is an expression that just writes to console, and as you can see, it's written directly in C#, but we also want to transpile it to F# code. So let's imagine we will have some F# transpiler class that we'll build in a moment, and by calling convert, that will return a string that contains the same code that we expressed, but in F# instead of C#. And to do that, we can use the visitor, and instead of just returning stuff directly, we have to provide some way to buffer the code that we generate. So we have a string builder for that, and we pass it through the constructor. And then as the visitor will go through the different expressions, we will build up the corresponding code in F#. And the visitor itself looks like this. So we have two methods that we overridden. So the one for visit lambda and visit method call. And we just want to make sure that those two are supported, because we're specializing on just the one type of expressions that write something to console, not trying to write a fully functional transpiler. And to do that, we only just have to catch those two expression types. And for lambda expressions, we just convert it to equivalent in F#, which looks similar, but it has the fun prefix and the as opposed to the fat arrow, we use the thin arrow with the dash instead of the equal sign. And for the method call, we just want to make sure that whenever we find console write line, instead of calling that, we want to replace that with printf function, and instead of just using the arguments directly, we want to separate them using spaces. And so this is how it works, and if we run it on the expression we've seen earlier, it will provide us with the code that resembles the same thing but in F#. And for example, if we decide to try it, we can use the REPL, put that in, and see that it works exactly the same. So it added two numbers together and printed it to the console. So this is great, and to summarize about expression trees, what we can say is that, first of all, they're really fun. There are a lot of cool things we can do with them. We can compile them in memory, we can infer them from code during compilation, do all the kinds of crazy stuff, but they're also used for really practical purposes. So for example, whenever we have some reflection-heavy code, we can make it a lot faster. Whenever we have to deal with late binding and we don't want to incur the performance penalties, we can use compiled expression trees to gain a lot of speed there. We can also use that to write our own runtime compiled DSL that is fast and also, as you've seen, a lot easier to do than to do manually. We can also provide refactor-safe identification for type members, so we use the statically typed system that C# has to do some meta-programming. And we can analyze specified lambda expressions and reflect on their structure, and even rewrite them to express something completely differently. And even beyond that, we can actually transpile it to other languages. So this is, for example, how Entity Framework works when it transpiles stuff to SQL. And if you want to, I guess, leverage the extension methods I showed earlier, there is the readable expression package that I've mentioned. You can find it on this using this link, but there's also another package that I wanted to mention, which is the fast expression compiler. I did not show it in this talk, but the way it works is that it adds another compile method, which is called compile fast, and that basically just removes some checks that normally you would have to do and makes the compile operation match faster in some cases. So that's just a way to speed up your expressions even more. In case you want to learn a little bit more about expression trees, you can also read my article that I've posted in April. This has a little bit more information on it. It's a little bit more in depth. And of course, if you just want to learn the API surface of the different classes that I've mentioned and how they work and stuff like this, the best place is to refer to the MS docs on docs.microsoft.com and start there. I hope you enjoyed this talk. I hope you learned something from it, and well, maybe you find some use cases for expression trees in your code. If that's the case, I would like to hear about it. But in any case, thank you for listening, and I hope you enjoyed it.